Okay.
All right, let's continue.
I think we can start. I will talk about semi-classical gravity. And of course, if you want to describe the interplay of quantum matter with gravity, you should use a full theory of quantum gravity. There are, of course, many attempts on the market about how to deal with quantum gravity. However, there are certainly certain regimes where one can use an intermediate step and to describe matter with quantum fields and at the same time consider gravity as a classical theory. Of course, the first thing you do in this kind of regime is to describe quantum fields which propagate on a curvature background. But later on, you also want to understand how the matter influences the curvature. And so you impose some equation, some backreaction equation. And the simple idea one can have is this one, to keep the Einstein equation with at the right hand side you have the expectation value of the stress tensor of some quantum matter in a fixed state. And of course, if you analyze things in this way, there are interesting effects which can be understood, which can be seen. For example, already in cosmology, just describing matter as quantum field, you can find that there are particle creation. And if you switch on this backreaction, if you're interested in describing backreaction, you get some already in this simple model, very interesting model of inflation. At the same time, if you are interested in black hole physics, when you describe quantum field propagating on a black hole information, you discover that there is this renowned effect called Hawking radiation. And if you try to couple this Hawking radiation if you try to understand the influence of this Hawking radiation on the curvature, you see that the black hole evaporate. And so all these nice effects can be understood in the realm of semi-classical gravity, and analyzing quantum field propagating on curved background and taking into account their backreaction to the curvature. Nevertheless, it is fair to say that there are many problems in this description. For example, the well-posedness of the dynamical problem associated to this equation is not fully understood. Maybe it's understood a little bit in some particular cases, for example, in the cosmological case, but certainly not in general. At the same time, since you are here equating things of different nature, I mean the expectation value of the stress tensor is just the mean value of something, so it's something of probabilistic nature with some classical quantity. Also, the physical consequences are still a little bit under debate. So it's not clear up to which regimes these equations can make sense. Nevertheless, let's try to assume this point of view and let's try to understand how this model how can we do some prediction with this model. And the first thing you have to do, you have to understand how to describe the right-hand side of this equation, namely how to describe quantum field propagating on a curved background and how to compute the expectation value in a certain state. And usually, for example, in the scalar field theory, we will see in short, you know that to get the stress tensor, you need to multiply the fields at the same point. And usually, this pointwise multiplication of quantum fields produce divergences. And so in order to get rid of these divergences, a regularization needs to be taken into account. And of course, a lot has already been done about the regularization of this kind of things, of this kind of observables. And here I have put some names of people that have studied these things already in the 70s, 80s, and 90s. What I want to say is that at some point, Bob Wald has given some requirements, some axioms that every regularization theory should have in order to have the chance of producing a meaningful stress tensor and a meaningful expectation value that can be effectively used in this kind of equation. And the interesting thing is that if you follow this prescription, if you try to understand what are the consequences of this axiom, you see that it is really possible to get expectation value of the stress tensor. However, immediately, since you impose that the expectation value of the stress tensor is covariantly conserved, you get that anomalous contribution pop up into the expectation value of the stress tensor. And this anomalous contribution are of geometric nature, essentially, and depends also on the coupling constant of the theory. And if you compute the trace of this object, you see that there is an anomalous contribution, which is usually called the trace anomaly. The freedom in the definition of the stress tensor and the construction of the stress tensor on curved space-time has been recently fully classified in a series of papers by Hollands and. But let's try to see a little bit what are the consequences of this anomalous contribution inside of the semiclassical Einstein equation. And as already told you, or if you are interested in cosmological models and you try to understand what is the effect of this anomalous contribution to the trace or to the stress tensor, you see that you can immediately get some model in which inflation takes place. Here I have in mind the renowned model of Starobinsky, where essentially this anomalous contribution causes or induces the presence of another de Sitter phase in the system at very early time of our universe. At the same time, maybe it's a little bit less known, the stress tensor anomaly can be used also to understand a little dynamic of the black hole. For example, in 2 dimensions, there is a nice work of Palbinot where it shows that the trace anomaly itself can describe the evaporation of the black hole. Later on, these 2-dimensional theories have been also studied by Ashtekar and other co-workers. This is what was essentially known and essentially understood till the 80s and the 90s. Now I am doing a very big jump in time, and I want to remind you some of the more recent results that have been derived in this kind of theories. For example, there are some exact results in the cosmological case. Actually, it is better understood how the dynamical problem in the case of cosmological space-time can be treated. There are at the same time non-trivial results which says how to describe systems where there is a large symmetry, for example, the spherical symmetry and some time invariant symmetry. Here I have in mind the boson stars and similar things. And even more recently, regarding the problem of black hole evaporation, the effect of the states have been nicely taken into account, trying to understand or trying to describe in a nice way the Gauss problem and its application to black hole physics evaporation. So this is essentially some of the results I wanted to mention. Later in this talk, I will come back to some of this and I will show you some results more concretely. But before doing this, I would like to mention what are the problems in the use of this semiclassical equation. As already told in the introduction, this semiclassical equation certainly is a bit problematic because you are equating, so cannot be a fundamental theory, because you are equating things of probabilistic nature with things that are classical. And so even if after regularization, the expectation value of the stress tensor is finite, if you try to compute or to analyze the larger or the higher order moments of this probability distribution, you get that there are divergences. Again, these divergences cannot be renormalized because these are divergences in the fluctuation, not in the stress tensor. Of course, things become nicer if you smear your fields. So the point is that this equation needs to be understood only after some smearing. A possible way out that I would like to mention is the one provided by stochastic gravity. And the idea with this stochastic gravity is that maybe the Einstein tensor itself is just the expectation value of the first moment of a probabilistic of distribution, this G, curly G, denoted here. And so in this way, you could also try to compute the higher moment and so on and so forth. And if you do things in this way, you can, for example, understand or see that there are some non-Gaussianities in this correlation function, and these non-Gaussianities could, in principle, play some role in the analysis of the cosmic microwave background. Another important problem with this kind of, with the solution of the semiclassical equation is actually the presence of the renowned runaway solution. And where are these coming from? And actually, if you compute the expectation value of the stress tensor, if you do a bit more careful analysis, you notice that in this expectation value, 4th order derivative of the coefficient of the metric appear, while on the left-hand side, only 2 order derivatives of the metric are present. And furthermore, if you do a careful analysis, this 4th order derivative of the metric are present even in a non-local way in this equation. So this equation is a little bit complicated. And then if you try to understand what is the effects of this kind of higher derivative present on the left-hand side, you see that there are cases where you find solution and then you modify a little bit the initial values of your solution to study what happens to fluctuation around this solution. And very often it happens that little variation on the initial condition produce exponential growing solution. This indicates in some sense that there are some instabilities present in this kind of equation. And for example, if you try to see if Minkowski spacetime is stable, actually you get that it is not stable. There are, here I want to mention the work of Horowitz, Walt and Flanagan, and Anderson about this problem. So in some sense, these runaway solutions are certainly problematic in the understanding of this semiclassical equation. Nevertheless, at least in some simplified model, one can recover stability, and maybe this is an indication that maybe further studies on this problem could be important. Okay. There is one last problem I would like to mention, and essentially it's about the comparison of this of the analysis of the semiclassical equation with a full quantum gravity treated with perturbation method, perturbatively. And essentially, a careful analysis of this comparison shows that semiclassical solution of the semiclassical equation correspond essentially to deal with full quantum gravity treated perturbatively. And in this full quantum gravity, you have essentially to discard the loop or to remove the loop diagram corresponding to the graviton, while at the same time you have to keep the loop diagram corresponding to matter. So in some sense, it's a little bit a strange expansion. I mean, if you have this perturbative treated quantum gravity and you want to recover this semiclassical gravity from there, this is not really a small parameter expansion, and at the same time is not really a loop expansion. So the solution or the regimes where the semiclassical solution plays an important role is still needs to be still understood and analyzed case by case. At the same time, a systematic comparison of the result of quantum gravity and semiclassical gravity have been recently initiated by Marcus Probe. Maybe you know these papers. Okay, and now after this very long introduction and after highlighting all this problem, let's try to see more concretely what are the kind of prediction we can get from this semi-classical Einstein equation. And the first thing I have to do is to remind you how to describe a quantum field which propagates on some curved background. And so maybe for many of you this is already known, so it's a sort of a revision of this theory, so be patient with this. So I will describe something for the scalar field. So I will consider only a quantum scalar field which propagates on a globally hyperbolic spacetime. So the kind of equation that this field needs to satisfy is this one. And this, if you see, there is the D'Alembert operator of our manifold M, of our spacetime M. And then there is this scalar curvature and the coupling with the scalar curvature. And this M is just the mass of the field. And of course, the quantization of this system is very well under control. It's just a linear theory, so it's just I have to describe just a linear quantum field, and it's not so problematic to assign the star algebra of observables to every globally hyperbolic space-time. And in some sense, this algebra of observables is nothing but the algebra generated by the linear field, namely the field which satisfies this relation I have written here. Most important is the fact that the field solves the linear equation of motion. The field is uncharged, so it's real. And then the commutational relation of the field are given in terms of the so-called causal propagator, which is nothing but the retarded minus the advanced fundamental solution of the classical differential equation provided by this object here. And furthermore, there is a very nice property. I mean, this quantization can be done coherently with respect of embeddings of globally hyperbolic space-time into themselves. So there is a general covariant. So this theory respects what's called the general covariance principle. Once you have one of these algebras on a fixed space-time, what you have to do is to get really expectation value, you need to introduce a state. And the state is nothing in this picture is nothing but a functional which is normalized, linear and positive, and which assigns expectation value to every element of this algebra. And as you probably all know, once a state is chosen, by J-ness theorem, you can represent the object of your algebra as a suitable linear operator on a fixed Hilbert space, and the state is nothing but a picked up normalized vector inside of this Hilbert space. Next step, in order to construct things like the stress tensor, is to understand how the state is precisely constructed. And in this kind of algebras I am discussing, we are working with algebra generated by linear fields. And so in order to describe the state, I have just to tell you what happens when I compute expectation value of products of these linear fields. And in particular, these products of linear fields are described by essentially endpoint function, which are suitable distribution over or suitable elements of the prime m to the n. And the next step is to, what we would like to do, we would like to include objects like the field squared and on, for example, the stress tensor inside of this object. And when you have to compute the expectation value of these things, as already mentioned before, what you have to do is you have to compute the distribution on different points. For example, here you just need the 2-point function in 2 points, and then you have to compute coinciding point limits. And usually these are distributions, so this coinciding point limit brings divergence in this case. So somehow we need a regularization prescription, and this normal regularization prescription should implement some normal ordering prescription. And the idea here is to use what is called the point splitting regularization. And in order for this regularization regularization to be meaningful, the state you are using needs to have some decent property. Namely, we would like to work with Hadamard state. And SK and Wald have taught us this, the two-point function of every Hadamard state can be written in this way. Essentially, the two-point function is divided in two parts. There is a singular contribution plus a smooth part, this W, and the singular contribution is essentially written in terms of this U and V object here. And this U and V are smooth functions, which are described by the geometry and by the coupling constant of the theory, so do not depend on the state. And then the singular contribution is described by the squared geodesic distance, which is present in this space. Epsilon is just a suitable epsilon regularization that you need to use in order to meaningfully define these objects. And the important point to mention is that in every Hadamard state, this function U and V are essentially universal. The only things which can change, which depend really on the state we are considering, is just the smooth part of the field here. And so the idea...
Excuse me.
Yes?
Can you hear me? Yes. I wanted to ask you a thing to be sure to have understood. Phi smeared by F is an actual function. But what do you mean by omega applied to phi squared of x is the product of distributions, right? When you say x as the argument is the point in the manifold, right? Not the function.
So phi itself is not a function, or better, it's a function with values in an algebra somehow.
Yes.
And but in order to give meaning to this object, you have to smear it, so to integrate it. At the same time, when you want to compute expectation value, like object of this kind here, you have essentially to take all your smearing function and to assign a number to all your smearing function. And you have to do it keeping linearity and some properties. And this object then is described by the two-point function of the theory, which is actually a distribution. So at the level, when you work with phi, these are essentially abstract objects. When you put an omega in front of them, you get a concrete distribution that you have to describe somehow. And here, when you write omega yx, I am just meaning the integral kernel of this distribution. Of course,
okay.
Integral kernel of generic distribution cannot be written in a precise form, but you can use, you can approximate it with a smooth function with the precision you like. And so this epsilon you have there is a sort of prescription to produce a decent function for this integral kernel. Of course, then the limit where this regularization is put in needs to be taken eventually, and when you take this limit, you get a proper distribution. Okay. Hopefully it was clear. Okay, but what is coming back to this regularization we have to do? We have understood that the two-point function of the state actually has a singular part which is essentially universal plus a part which depends on the state. And so now the idea and this singular part essentially can be constructed knowing the geometry at one point and in the neighborhood of this point. So the idea is that before computing the coinciding point limit, one has simply to remove this singular contribution. If you do this in this way, what you get when you compute expectation value is that you get finite quantities. The nice things to remember is that this way of doing the regularization reduces to the ordinary normal ordering in flat space-time. So this appears to be the nice thing you have to do. At this point, with this idea at the end, we can really use or take this other kind of observables, normal ordered of course, and add them or use them as generator together with the linear field. In this way, we are essentially extended our algebra of observables And this extended algebra of observables takes also into account the stress tensor. Let's see how it works with the stress tensor. So the classical stress tensor has this form, and now we want to compute the normal order of the version of it. And so the idea is simply this one. Notice that the classical stress tensor can be seen as a certain differential operator applied to two fields at 2 points. And then if we take the coinciding point limit, essentially we really get the classical stress tensor. So when we compute the expectation value, the idea is simply this one. We have to subtract the singular part to our 2-point function. We apply our differential operator, and then we take the coinciding point limit. In this way, we have computed the expectation value of the normal order or regularized stress tensor, and this gives certainly a finite quantity. As you all know, in this procedure, there is an ambiguity. So there is a renormalization freedom. We are essentially subtracting infinities. So at some point, we need to take care of this renormalization freedom. Nevertheless, this renormalization freedom is fully classified by Hollands and Wald, and it can be fixed in part by the requirement that the stress tensor you get, the expectation value of the stress tensor you get is covariantly conserved, but it is not completely fixed. Nevertheless, as already mentioned, the price to pay is that an anomalous contribution appears in the expectation value of this stress tensor. And the trace of this anomalous contribution is not vanishing in general. So, and it's a classical non-vanishing object. But let's see more concretely for the trace of the stress tensor. How can we understand, or how, what's the form of this expectation value? And essentially, as I told you, this stress tensor is characterized by, or the contribution to the expectation value of the stress tensor can be characterized by 3 objects. There is an anomalous contribution, there is a contribution which is about the normalization freedom, and there is a state-dependent part. This state-dependent part needs to be discussed carefully. But what we have is that the anomalous contribution can be essentially written this way, and here you see that there are components which depends on the coupling. There is the square of the scalar curvature, and there are other contributions that can be obtained using once you know the curvature tensor of your space-time. Regarding the renormalization freedom, this is described essentially by 3 parameters at this level, and these 3 parameters are not fixed by the theory. These are renormalization constants, so needs to be fixed by experiment. And essentially, one of them corresponds to changing the cosmological constant of your space-time. Actually, the stress tensor is changed by a constant. The trace of the stress tensor is changed by a constant. Here, the trace of the stress tensor is changed by a contribution proportional to the scalar curvature. And then there is the last contribution, which corresponds to the D'Alembert operator applied to R multiplied by a constant. The first contribution corresponds, as already said, to a renormalization of the cosmological constant. The second contribution corresponds to a renormalization of the Newton constant. However, the third contribution is a purely quantum object, a purely quantum, let's say, renormalization constant that depends, that gives contribution proportional to box of R into the trace of the stress tensor. Nevertheless, up to these coefficients, the form of this renormalization freedom is known, and also the anomalous contribution is well understood. There is, nevertheless, at the level of the trace, also a contribution which depends on the smooth part of the Hadamard singularity, of the Hadamard 2-point function. And this smooth part is understood as usual as the coinciding point limit of the 2-point function minus the Hadamard singularity. And now let's try to see what is more precisely the effect of this anomalous contribution into the expectation value of the stress tensor, and then their coupling to the scalar curvature. So let's start considering a cosmological space-time, and a cosmological space-time is just a word product of a three-dimensional manifold times an interval of time. And the metric you have on this manifold is just minus dt squared plus, at least in the flat case, you have the Euclidean metric multiplied by a scale factor A of t. This t is the cosmological time, A is the scale factor, and a quantity which is very important in this analysis is the Hubble parameter, which is nothing but the time derivative of the log of A. Later on, we will use also the conformal time, and the conformal time is a definition of the time of the theory, which makes our manifold manifestly conformally flat. What's important to know is that if you want to work in cosmological space-time, then what happens is that you have reduced your degrees of freedom to only one. I mean, the scale factor is the single freedom you have into this metric. And so you have one single freedom, and at the same time, in the geometry, and the other freedom you have is the notion of the state in the quantum part of the theory. And the equation you need to use are essentially the following. You need to assume that we need to have that the stress tensor is covariantly conserved. Then we have the equation for the trace of the semiclassical Einstein equation, and plus an initial condition, namely we have to fix the G00 component equal to the expectation value of the 00 component of the stress tensor at time 0. And what we want to do, we want to look for existence and uniqueness of the solution of this system. And let's start analyzing what's the form of this trace of the semiclassical equation. And we see that in terms of the Hubble parameter and in terms of the derivative of this Hubble parameter, when the mass is larger than 0, when the coupling to the scalar curvature is 1/6, and if you assume that this beta-3 disnormalization, one of these normalization freedom is set to 0, the equation becomes very simple. So it becomes essentially a sort of differential equation for H plus a source term which depends on the expectation value of this phi squared. So the quantum state is not disentangled by this equation, really enter into this equation with this expectation value. And so we would like to understand at the beginning what happens if the expectation value of the normal order at the phi square is 0. And this is in general impossible. Nevertheless, we could assume that it's 0 for the moment, and then we can try to understand what's the form of the solution of this system. And in particular, if you fix your phi squared to be 0 or to be proportional to the freedom you have, then what remains is essentially a differential equation for H that can be solved. And in particular, let's try to see what are the fixed points in H of this equation in the Hubble parameter. So let's plug in also H dot equal to 0. And in this case, you get an equation which has this form. And this equation can essentially be solved. And there are essentially two contributions, two constants. One, which is essentially more or less the cosmological constant of the theory, and the other one which depends on this parameter you have here in this equation. And this parameter is nevertheless, to try to do some computation, this parameter is very large, and it is of the order of 10 to the power of 44 second to the minus 1. So it's essentially the inverse of the Planck time, so very large contribution. And now you can also you can try to understand what are the solution of this system, and then you can drive a picture for the solution of this form. So if Here we have the time renormalized with respect of this new large fixed value of this h we found before. And then we see that there are essentially two fixed solutions, one which correspond to h squared equal our lambda, and the other one which correspond to h equal this h plus, which is the inverse of the Planck length. And if we try to compare this equation with the kind of model of cosmological model obtained with classical matter, essentially we obtain that in this regime, the black line which corresponds to this quantum solution is very close to this red line, which is nothing but a universe filled with radiation. And in this region, the solution is very close to this blue line, and this blue line is a universe with radiation at a cosmological constant. And so this, you see that there is essentially another cosmological constant popping up into the system. This kind of observation was already present in the 80s, and essentially this is the source of the Starobinsky model of inflation. Okay, and in this, so I wanted, you see that this semiclassical equation treated in this way produces the presence of other stable de Sitter spacetime. Let's move on a little bit and let's try to see, keeping the same degree of approximation, what happens in the case of black hole physics. And now we are changing a little bit the perspective. We are considering a star which collapses, and we assume spherical symmetry, and so our stars form the black hole. Here I have depicted the Penrose diagram of this situation. So in this direction there is the time, in this direction there is the radius. This region corresponds to r equals 0, and every point corresponds to a sphere. And this grid line corresponds to our star, which is shrinking. And at some point, when the radius of our star becomes smaller than 2m, an horizon forms, and so a black hole is formed in this case. And usually outside of the star, in this picture, we have vacuum situations, so we don't have matter. At the same time, the metric, since we are in a spherically symmetric situation, the metric outside of the star by Birkhoff theorem correspond to the Schwarzschild metrics. And then, but we all know that if we add quantum fields which propagates on this background, what happens is that this picture is essentially altered. Classically, nothing can escape from the black hole, but on the other hand, if we consider quantum matter propagating in this space-time, even if we assume that our quantum matter is in a vacuum state, very far from the black hole in the past, what happens is that if we look here at this region and we take a detector, we point this detector towards the center of the collapsing star, we detect that some flux of quantum particles are emanated from the black hole. And this flux of quantum particle is just the renowned Hawking radiation. And if we look at the spectrum of this Hawking radiation, we see that in the frequency spectrum, we recognize the known Bose factor with a fixed temperature, and this temperature is fixed by the surface gravity divided by 2 pi. And furthermore, we can also compute the power of this energy radiated at infinity, brought to infinity by this flux of particle, and this power has essentially this form. And so there is an energy coming out from the black hole, even if our matter in the past was in the vacuum. So where does this energy come from? And so the idea is that this energy comes at the cost of the mass of the black hole. And so if we think adiabatically and we equate the variation of the mass with this power radiated at infinity, we get essentially that the mass decreases with this law. So the third power of the mass decreases linearly, essentially, in time. And the degree of decrease is essentially described by this coefficient present in front of this radiated power at infinity. And so the very end, what you get is that, according to this equation, the matter at some point fully disappears. And so this means that there is this radiation with this matter which decreases in this adiabatic process. At some point, the matter completely disappears. So here you have a situation where no matter is the black hole as vanishing matter, no matter anymore. So you get essentially, again, flat space-time. So this is essentially the Penrose diagram of this situation, and the Penrose diagram, which is usually drawn in these things. However, it is fair to say that this kind of diagram are described or are done or are guessed on the basis of this adiabatic thinking. For example, the precise form of the space-time near when the evaporation takes place is still not completely understood. And in fact, it would be nice to understand a little bit better if this kind of process could be, for example, obtained without imposing by hand this kind of equation and getting this kind of evaporation only, for example, from the semiclassical equation. Let's see a little bit what can happen. And actually, if we assume now that our space-time is in such a way that we have a mass that can change with respect of this other coordinate, namely we assume that our space-time is in a idea, is described by a idea space-time, then the metric of this idea space-time is this one. And essentially, this is like Schwarzschild space-time where the mass changes with this null coordinate v here. And so we can now try to compute the trace anomaly of massless conformally coupled phase matter in this system, and we get that this trace anomaly as a form which is proportional to the mass squared divided by r to the power of 6. And now, in this kind of space-time, the UV component of the geometry is 0. So if we discard this contribution, at the same time, the stress tensor is covariantly conserved. So this equation gives back an equation for the evolution of the mass. So assuming that this is 0 in a certain state, again, an assumption which I am not able to verify fully, but assume that you are in this situation, that what happens is that this equation produces a variation of the mass, again proportional to some of the coefficient present in this trace anomaly. And so we have simply imposed our semiclassical equation here, and we obtained that our black hole evaporate, and essentially the rate of evaporation is very similar to the one we have seen with this adiabatic thinking. Of course, this is again an approximated way of thinking. In order to improve this situation, we need to better understand what is the form of the two-point function of the theory in this kind of metrics. We have to analyze the standard regularization of this system, and then we have to compute the expectation value and take care of this expectation value in our system. This is certainly not an easy task. Nevertheless, it's in respect of these problems, I want to mention the nice result recently obtained by Rainer Fehr and Dan Jansen. So things are improving some. Okay, and then in this last part of the talk, I would like to describe some more mathematical feature of this semi-classical equation, and I would like to highlight or to underline some of the mathematical problems that are present in the treatment of this equation. And in order to highlight this problem, to explain this problem, I will consider a simplified model. And in the simplified model, I will fix my space-time to be Minkowski, and I will consider two fields over this space-time. One of these fields is treated quantum mechanically, or it's just a quantum field, and the other field is just a classical object. So the quantum field is this phi, and the classical field is just this psi here. And essentially, you see in this equation, the psi plays the role of an external potential for our scalar fields. And so this psi is this classical external potential, but we want to impose a sort of semi-classical equation. And we say that our external potential is essentially a constant, which is known, plus the expectation value of our quantum field square. So we impose this equation. So this is a sort of prototype of the semi-classical equation in this case. I think that a similar model has been studied by Benito, by Bernard and others, if I am not mistaken. And so I will try to give some hints of what are the problems in this kind of equation. Okay. A possibility, of course, is to fix at the beginning this psi to 0, then quantize the system, then find a state and compute the expectation value of this phi. Then we can update our psi and then go back to the original equation, use this updated psi into this equation, so we can compute again our quantum field with now the external potential psi. We can again fix a state and compute again the expectation value of this phi square. And if we operate in this way, essentially we get a recursive procedure to get hopefully closer and closer to the solution. However, it is not at all guaranteed that if you apply this recursive construction, you really end up with a full solution of the system. And in order to understand what happens, it is maybe useful to use a little bit of perturbation theory. So now we treat for the field phi this contribution as coming from an interaction Lagrangian of this form. Maybe a parameter 2 is missing here, but it's not so important. And so we have our Lagrangian of the system. And once you have this interaction Lagrangian, you can use the standard technique to understand how does our phi square changes in the system. And in particular, using standard renormalization technique, you get that the expectation value of the interacting field phi square is just 0 in the background plus some correction. And the first linear correction has this form, where here you have the square of the Feynman propagator, and here you have the square of the two-point function. Of course, to compute the square of this Feynman propagator, you have to use a normalization, so I have implicitly done it. And then this is the linear contribution in psi to this expectation value, and then there are higher order contribution. Suppose we discard this higher order contribution, and then we plug in this object here in our semi-classical equation there. So what we get and we discard the contribution which are nonlinear, and then we get something of this form. And so this equation has the form of a fixed point equation, where we have psi equal to a constant plus an operator applied to psi itself. However, here now, in order to understand if this procedure can have a really fixed point, if this equation has really fixed point, we need to understand something more about this operator tau present there. And a closer analysis shows that essentially this tau here, or the integral kernel of this tau here, is proportional to the logarithm of the retarded propagator of the free field. And then the most singular contribution of this retarded propagator is this one. So it is a little bit like the Hadamard singularity plus box of the logarithm of sigma. So it's a bit more singular than what you have in the Hadamard singularity. But even more closer analysis shows that if you compute the extremum, the supremum of t applied to psi, there is no chance. In order to control the supremum, you need to use, or you need to have the supremum of the psi and the supremum of the derivative of psi. So essentially, in order to control the supremum of t psi, you need to know the derivative. In this case, essentially, you say that your operator loses derivative. And so usually when you have this kind of operators which loses derivative, the fixed point equation you have above cannot be easily studied with Banach fixed point method or similar things. So you have to invent something else. And so what you can do, you can try to analyze, or you can try to study or to see if this operator tau has inverses. And actually it happens that, at least in the cosmological case, it is possible to prove that this tau has nice inverses. And so suppose that this inverse of tau exists, and suppose that this tau has nicer property, and then you can rewrite your equation essentially in this way, applying tau to the -1 on all the things, and use some fixed condition. And this is another fixed point equation you can get in this system. And actually, a more careful analysis shows that while this t loses derivative, this t to the -1 is actually a continuous operator. So this means that you can, in principle, use standard theorems or standard analysis to understand what happens in this case. And actually, it turns out that if you restrict your interval on time where you want to analyze your system, you really get that in this way you get, you can prove that on short intervals of time, this tau to the -1 becomes a contraction, so you can use Banach fixed point theorem to get the solution. It is fair to mention, or it's important to mention, that similar problems have been analyzed are known to be present, or are already known to be present in some literature. And it's important to mention that there is another possibility. I mean, here in our work, we try to use this idea to construct the solution of the semiclassical equation. In other words, it works instead of computing the inverse of this operator. People tried, and in particular Arno Gottschalk, Daniel Simpson, try to put the semiclassical equation into a system of, into a dynamical system for all the moment of the coinciding point limit of phi, Laplace operator to the power n applied to phi. In this way, you get an infinite number of differential equations that can, in principle, be solved. Okay, I think I was slower than expected, so I just want to show you this this theorem. So let's come back to our semiclassical equation for the in the cosmological case. And remember that there is only one degree of freedom, which is the scale factor, and we have this equation. And then essentially, it happens that in this trace of the stress tensor, there are derivative of the scale factor up to the fourth order. In the T00 component, there are derivative of the scale factor up to the third component. And now we see that the first equation is satisfied because of the chosen renormalization procedure. The third equation can be fixed if you carefully choose your states. So if you have the derivative of A up to the third order, I can produce a state which is regular enough to give back the stress tensor everywhere spacetime and regular enough to satisfy this constraint equation. And then the second equation, after a careful analysis, can be shown or can be treated with technique I have just discussed. I mean, just writing it as a fixed point equation with some operator which is not continuous in the topology you want to use. You can nevertheless invert this operator, and the inverse of this operator is nicer. And actually we have this nice theorem. So the second equation can be put into a form of a fixed point equation that can be treated with Banach fixed point theorem for the third derivative of the scale factor. Given the initial condition, you can get the state you are considering. So all in all, for sufficiently small time, you can prove that solution of that equation exists. Okay, so let me just conclude with some final comments. We have briefly seen in this talk that semiclassical Einstein equation have interesting implication, at least in cosmology or for black hole physics. Nevertheless, it's fair to say that the physical well-posedness of this equation, or the regime where this equation is physically well-posed, needs still to be understood. There are this runaway solution that has to be kept in mind. And at the same time, the mathematical well-posedness of this equation is essentially established only in very few cases. So it would be nice to understand if also in more general context, one can get some theorem which tells you that a solution really exists. At the same time, would be nice to have an exact model of black hole evaporation. I mean, there is still work to be done to get something of this form. So essentially, this is all I wanted to tell you. So thank you very much for your attention. If there are questions, we'll be happy to answer.
Let's thank the speaker. And if there are questions, please raise your hand virtually. So Sebastian?
Ciao, Nicola. Thanks for the talk. I was wondering, the appearance of these pseudo-differential operators, like log of delta, is that depending on the state, on the Bakuman state that you are considering?
Okay, we have carefully analyzed this situation in the cosmological case, and I can say that this operator is not dependent on the state itself. The state-dependent part, the state-dependent contribution are always more regular than these things. So can really, usually this goes into the correction I have discarded, and these are usually gives continuous operator.
Okay, thanks.
Bernard?
Oh, yeah. Hi, thanks. That was a very nice talk, Nicola. You covered a lot of ground. I just wanted to ask about this model with the phi and psi. I think we're looking at the right page. I was confused why your formula for the second line, second equation that you're displaying now. Why you've got that
This
equation? I would have expected an equation that looked like box acting on psi is some coupling constant times expectation value of phi squared.
Okay. Okay. So this is the equation I have imposed, and I think that this equation is closer to the semiclassical equation for the things I'm going to say. Usually, here you have the scalar curvature in the cosmological case, and so usually you have some box of R contribution in the semiclassical equation, and at the same time you have in the expectation value something which is proportional to phi box of phi. So in order to keep some feature which are present also in the semiclassical equation, I have decided in this model to remove these two boxes.
Ah, okay.
Okay. So
Interesting.
if I'm trying to, if I would like to use the semi-classical equation, I will have some boxes here and some boxes also inside of this expectation value.
So it's a sort of the philosophy is you want something simple so you can actually prove a
Yes,
result.
yes.
But you
So
still
this is,
think it reflects some of the features of the
exactly.
cool thing. Right.
Exactly.
Yeah, sorry.
But let me say that I used this simplified model just for this presentation. In the analysis we have done, we have really used the full traced semi-classical equation with all the boxes put in the right place.
Okay.
So this was just for this talk, to make things simpler. Because I wanted to highlight the problem in the treatment of this equation in a simplified model.
Okay, thanks. So is there a paper that that's
No, I don't have a paper for this simplified model. I have a paper for the full semi-classical treatment, where essentially the same features are present with all these boxes and so on and so forth.
Okay. What year is that, please? Just to
it's with Paolo Meda and Daniel Simpson and myself. There is only one.
Okay. I'll look at that. Thank you.
Okay, but you will not find this model in there. I mean, you will find the full semi-classical Einstein equation there.
Right, I get it. Thanks.
Okay.
Claudio?
Yeah, thank you very much, Nicola, for your nice talk. I have actually a question as soon as I can turn on my video, now. A question concerning your last result with Paolo on the fixed point theorem. Can you show me the slide? I think it's the one before the last. Okay, this one. So what I was wondering is that you can prove that the third derivative of A is continuous, which means that you can get a regularity of the scale factor telling you that it's C3, it's 3 times differentiable by integrating. I'm wondering, is this regularity just the best we can do with the fixed point theorem, or is there something, let's say, more substantial on the fact that we have to expect the scale factor to be exactly in that class of let's say, functions?
No, I think it is just for the system we have taken. I mean, the way in which we have analyzed the system, we have seen that you have, in this case, third order derivatives of the scale factor available. At the same time, a more careful analysis of these things shows that the solution is actually piecewise C4, and this is important because at some point in some component of the stress tensor, you need to take also the fourth order derivative of the metric. And furthermore, this result is with this regularity only because we wanted to be as simple as possible. In order to improve it, we needed to do more carefully the selection of the state we are to consider in our system. Okay, but thank you for this question. Because of this C3 regularity, our solution can be understood as a weak solution of our system of equations somehow. So we don't have fourth derivative available. At the same time, the equation, okay, and you get this third derivative only because we inverted this operator I've told you before. It's actually.
Yeah. Okay, thanks.
Any more questions? All right, so let's thank Nicola again for the really nice talk.
Yeah,
thank you, Eleni.
Our next speaker is going to be Eric Curiel in the first Monday of March. So if you're not on the mailing list, please subscribe on the website, on the mailing list to get all the Zoom information, the information about the talk. So I hope we can see you all there.
Okay, thank you very much to everybody.
Thank you, Nicola.
And I hope
thank you,
to
everyone.
meet you soon in person somewhere.
Yes. Okay. We can stop the recording maybe now, I think.